Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is Narrowband Dielectric Frequency Response, application on high voltage and extra high voltage OIP bushings. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as a moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Dr. Diego Robolino, Business Development Director for Power Transformer Testing. Also, to assist with the question and answer session, we will have joining us Jill Duplessis, Technical Marketing Manager, and Sanket Bolar, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Dr. Robolino.
Well, good morning, everyone. It's a pleasure to be today running this webinar. It's a very interesting topic. I hope everybody's going to enjoy the presentation. We're going to be looking into bushings, especially into OIP bushings. You understand that those are the majority of the bushings installed in the field, and that's the reason why we're focusing on those. So just a little agenda. We're going through some background motivation for this presentation, some theoretical fundamentals, then we're going to go in depth into the diagnostic methodologies that we have for OIP bushings, what is for the field as a routine testing, and what is advanced and non-intrusive methods. And then we're going to talk a little bit about the field challenges that we can encounter doing some testing of high voltage and extra high voltage bushings, and we will run some conclusions out of it. So let me start with the background. It's interesting on all the presentations that I try to provide here. I will always try to make a reference to international documentation, technical work that has been provided by different working groups, in this case, SIGRE, published in 2015, a document showing the importance of bushings in the overall transformer reliability. And you can see, for example, in this report that a big number of transformer breakdowns were caused by bushing failures. So it's not always the transformer itself or its internal components in the coil winding core assembly, but it could be some of the accessories that we have for it, in this case the bushings, that may act as part of it. So keep in mind that there's several documentation that is leading towards the application of different techniques for improving the reliability of bushings. After this work that was published in 2015, in the beginning of the year in 2019, SIGRE published a different document talking specifically about reliability of high voltage bushings. And this is a very interesting work that I suggest everyone who is involved in asset management and maintenance of these devices to look into and have a good read. As you can see in the chart on the right-hand side, it's about 16% of the failure modes that we have for transformers that are directly related to the bushings. So this gives us an idea of how critical maintenance, monitoring, diagnostics is related to bushings. One of the things that you have to remember is a new insulation system is dry, and this condition is sometimes difficult to keep. For bushings, I think that moisture has not been one of the biggest problems reported on the failure modes, but we need to understand how important is the influence of moisture in any kind of failure mode. So the ingress of moisture could be through seals. There might be formation of moisture from degradation of the paper as part of the aging process. There might be formation of gas from partial discharge activity inside the bushing. And of course, sometimes we need to overload our system. We may have a fault in the system that will create a formation of carbon deposits in voids inside the insulation system. Keep in mind that like any organic material, paper and oil that is inside these bushings tends to age. So aging is a one direction process, right? And we need to understand that aging is not only because of thermal effects, it's because of the normal operation that we have. It's because it's working at high voltage and extra high voltage stresses. So despite the technological advances, aging will always be in place in our electrical equipment and high voltage apparatus. What do we need to do? So we need to be proactive, right? We need to take necessary measurements to avoid critical failure and to be able to determine when to take different actions. What kind of actions can we take to improve the quality or to avoid damage of major equipment that is related to these bushings? So what are we trying to look at this is, if you look at the bushing has no sensor added to it, right? The only type of sensoring that you may see in the bushing by construction is only the liquid level gauge, right? You can see probably what the level of oil is inside the bushing, but that's all you can see. There's no other instrumentation mounted. So the idea is to keep the insulation system inside the bushing as it came from the manufacturer. So we prefer to have non-intrusive and non-destructive methods to do the analysis. We try to minimize any hazardous conditions during the testing process. And one of the big challenges that we have is, of course, this is a low capacitance object. And if you go to high voltages and extra high voltages, the effect of the electromagnetic induction in the substation, of course, will create some noise that we need to overcome in our testing procedure. With that being said, let's look a little bit into the construction of the bushing itself. One of the interesting things is that these condenser type bushings are basically produced by wrapping paper, right, or synthetic material nowadays, on a central tube or conductor. This is created with electrodes, which are basically painted with conductive ink, or we have also some metallic foils, could be aluminum foils, different lengths, which are inserted in this wrapping that we have for the insulation system, for this condenser type. As you can see here in the design, we will see different distances creating these capacitors. And one of the interesting things about it is that we have selected, or we have designed the bushings in a way that we have two different capacitances. One that reflects the majority of the insulation system, which is called the main insulation C1, which basically goes between the central conductor, which could be the central tube that we have for the bushing, depending on the type of design, of course, or a draw lead. So we need to understand the different construction types of bushings that we have. But basically, it will go between the central conductor all the way to the tap, to the test tap. And this is one point of discussion, probably, and to better understand the condition of this tap, you may find two different types of taps. One that we call the test tap, right, which is basically connected to the last layer, to the last electrode that we have in the C1 insulation system, right? And the other one that we call the voltage tap or capacitive tap. There is a little bit of difference here, and you need to be clear on what kind of tap you have on your transformer, because sometimes people will go into the question, do we have to test the C2? And the answer will be going into, is this a C2 for a test tap or for a voltage tap? And nowadays, especially in North America, it's pretty common the use of a voltage tap, and that voltage tap is connected probably to some monitoring devices, is connected to some additional instrumentation probably. And now that brings also a point that could be damage in the system as well, or it could be stressed by different transients in the system, or it could be stressed by other power system transients. In that way, we need to understand what is the idea of having a bushing. The bushing main roles as defined in SIGRE 755 are to insulate the high voltage to tank, to conduct load current, and to separate insulating media. And you can see that you can go from oil, air, oil, SF6, air. There's different constructions. There's indoor type of bushings, there's outdoor type of bushings, and you need to recognize those. You can, of course, you can recognize because of the design, the construction, the type of the sheds, etc. And in these different designs, I think that historically, we can look into the construction, of course. The first ones were very solid insulation manufactured for lower voltages. But as the voltages were increasing in the system, right, the type of insulation system for bushings was also being developed and evolved. And you can see, for example, we started with the RBP, which is the resin bonded paper type. And then we got into the OIP type of oil-impregnated paper, from OIP into RIP. And nowadays, we're trying to eliminate as much as possible the influence of mineral oil and sometimes of the paper, trying to reach greater hotspot temperatures, right? And we're getting into more systems like the RIS, which is basically replacing the paper for synthetic material. Therefore, we need to look into the diagnostic methods. And let's look first into the traditional testing that we have. When we look into the traditional testing, right, one of the most important things, I guess, for any person who's going to do a test on a bushing is to run a visual inspection. Visual inspection, just go around the bushing. If you open the test tab, make sure that there's no corrosion, that there's no fungi, that there's no oil leaks. That is very important before you even start any testing procedure. Make sure that you have enough level of oil, right? Sometimes we have not noticed, and that level gauge that we have on the bushing may not show us properly the level of moisture. So make sure that you take enough time to run a visual inspection of the bushings when you have the opportunity to do that before any testing. The other thing that you can do, of course, is a thermal scanning. And that is very interesting to do, of course, in the sense that with the thermal scanning, you can see any type of issues with connections, right? External connections, especially if you have a power line being connected from your switch yard to the bushing. And if there's any loose connection there, right, that will create a hotspot, and that hotspot can derive into, you know, additional issues with the operation of the system. So visual inspection, thermal scanning is one of the easiest things to do. Actually, it is recommended to do visual inspections at least once every 6 months, right? Try to be careful, of course, on this, but see what is going around. If there's any leak, probably on the top of the transformer, and on the top of the tank that may be coming from one of the bushings, try to look if the level of the gauges is okay. Then something else that is especially not very much recommended, and not something that everybody likes, but it is done, especially on extra high voltage bushings, is to take a sample and do some DGA. So you look into gases, of course, and the same principle of analysis. Could be different methods, of course, for the analysis of the dissolved gas in the oil, but you can take a sample. You can send that information, you can send the sample to a laboratory and get the analysis from them, and you will be able to detect, right, if there's any gases that may reflect any active failure condition, okay? And one of the most important things that you want to make sure you don't have in your bushing is any residues of PD, right, of PD activity. You want to make sure that there's no PD activity, because PD may derive into byproducts like X-wax and things like that, that will create sooner or later damage and possible destruction of your bushings. So, and again, the VGA is only possible in OIP bushings, of course. And then I think that we have to emphasize the value of capacitance and term delta testing, or power factor testing. Typically, what we do is a line frequency, or what we call the 60 hertz or 50 hertz, depending on where you are. You do a test at the temperature that you are running the test. You know, in different activities, I have asked attendees, how many of you have tested a bushing at 20 degrees C? and I've never seen somebody raising the hand, which tells me that you're always testing at different temperatures, right? And actually, it's very interesting the way that you determine the temperature of the bushing, because there's no sensor. As I mentioned before, there is no thermal sensor to tell you what the insulation temperature on that bushing is. And when you start looking into this, how will you determine this temperature? So some of the recommendations given in different literature is talking about taking, for example, an average between the top oil temperature of your transformer, right, and the ambient temperature, and make an average of those two numbers. That is one approach. The other one, for example, proposed by Segre, is to measure the temperature at the bottom flange, right, and to measure the temperature at the header of the bushing. And again, you take an average between those two, depending on the length of the bushing. Segre has a little bit more complicated equation, but at the end, it is a tough question to determine exactly what is the temperature of the bushing, of the insulation. We are not concerned about the ambient temperature. We're not concerned about the temperature of the transformer. We are concerned about the temperature of the internal insulation, right, under the upper envelope of the bushing. So this is critical, and you have to take into account that whichever way you decide to proceed with the temperature measurement, that has to be for everybody in your company. That has to be the plan for everyone else. So you're consistent with the data that you get, okay? Sometimes I've seen people just reporting top oil temperature. Sometimes people just reporting ambient temperature, and those might be misleading. And remember that capacitance and tan delta on OIP bushings is temperature dependent. So temperature has an influence on it, and especially when we have aging processes going on, accelerated aging sometimes, or increase of moisture, or any kind of changes in the insulation system, temperature will have a different effect as compared to a newly manufactured bushing. So from that point of view, I want you to look at this chart, and you can see clearly that out of the study carried out by Segre, 96.7% of the utilities that were surveyed, they ran a capacitance and tan delta test at line frequency. That is very typical for them. The next test that they have is the infrared testing, or the infrared scanning. And then, because there's lots of high voltage and extra high voltage bushings in the OIP world, you will see that DGA fits into the third category. A little bit lower below that, we have moisture in oil. And you can see that after that, we have different frequency and I would say dielectric response, more than just frequency, but dielectric response methods that may add up to another 20%, 30% of the categories. But interesting enough as well is that how often these utilities are running a test on the bushings, right? Offline testing on the bushings. And you can see clearly on this chart here that in average, I would say that the 2 to 4 years is an average number. So it's telling me that utilities at least once every 3 years are running a test on high voltage bushings. I hope that every time that you have the opportunity to run a test on your bushings, you do it. The other reason is because your power factor value could be a first indication that you need to look also at the bushing. And I have seen many times that because we are rushing in the field, because we don't have enough time, we do the power factor testing on the transformer, right? And then we say, okay, we got an increased value here, but we need to re-energize the transformer. So, okay, let's re-energize, and then we look into these values. And once you re-energize your transformer, you cannot go back to your bushings. So this is critical. This is important. If you see changes in your power factor, especially when you're looking into capacitances from high to ground, low to ground, where of course the influence of your bushings is there on the power factor measurement, you need to look also at your bushings, because one of those may have something else to tell you in the diagnostic process. Okay, so let's look now into the advanced non-intrusive methods that are available nowadays. AC insulation testing, as I was mentioning to you, is extremely important, and is, as you saw on the chart previously, it's one of the is the first and the most important test that we are doing. First, because it's telling us, right, what the condition is and how reliable is the use of this high voltage piece of equipment. Then it allows us to detect before permanent damage done. It allows us to detect any potential issue that is going on, and of course prevents accelerated aging of the system. So this is part of our proactivity, right? I want to emphasize on this. We want to be proactive, not reactive, right? When it's done, it's done. It just if it exploded in the field, if you had an explosion and it's broken, it's damaged, that's it. It's catastrophic failure that might have affected not only the bushing but also your transformer and maybe some systems and equipment that are in the neighborhood of these bushings. And you can see on different reports that little parts from the explosion of a porcelain bushing will go as 100 yards, 150 yards away from the explosion. So it's very risky, especially if you have people in the substation walking from time to time, doing typical inspections or maintenance activities. So we have to be careful with this, and the more proactive we are with our bushings, the better we are with the safety and health of the system. So what do we do? As I was mentioning before, we have C1 and C2 capacitances. When we look at the C1 capacitance, what we do is we energize with AC voltage source, right? And we inject to the main conductor of the bushing. Right? We apply the voltage to the main conductor of the bushing, and we measure through our test tab or voltage tab, okay? So again, the recommendation, look into the tab, make sure that you have a good connection, make sure that you are not touching ground, because if you touch ground, then your testing equipment will trip, basically. Make sure that everything is grounded. So the flange, the bottom flange, should be well connected to the tank, and that's something else that you can double check. Make sure that you have a good connection to ground from the bottom flange of your bushing, and make sure that you have a good connection to ground. When you do the C2 test, you will swap the leads. Basically, you will inject voltage through the test tab, and you will measure through the central conductor. And actually, the measurement will be through ground, because this is a GST. So this red lead here will be on guard, okay? And the measurement will be on a GST, right, through ground. So the ammeter will be there. Okay, so when we're looking into the high voltage oil-impregnated paper bushing insulation, we can see that between 5 and 50% of transformer failure is related to bushing failure. Okay, that is one part. The insulation of these oil-impregnated paper bushings, right, is conformed of these two groups, the C1 capacitance and the C2 capacitance. Most of the people are always asking, well, do I need to do a C1 test? Do I need to do a C2 test? And I would say, if you have the opportunity to do both, do it, okay? And one of the great things that we have about power factor testing is that we can do some trending analysis, okay? But remember again that power factor testing, tan delta testing, is temperature dependent, okay? So a good temperature measurement, a good reference, a good correction to 20 degrees C, so you can compare and do a proper trending, is absolutely paramount. So the other thing here is that, how do I assess the information that I get? And we have, according to the standards and the technical references, we have basically different values. If we look, for example, for service age bushings, right? We have a tan delta, or a power factor, at 20 degrees C line frequency. And through the presentation, you will see, for example, the tan delta, or the power factor, with a 20 here refers to the temperature, and LF refers to line frequency, suggested to be below 0.7% according to IEC, or below 0.5% according to C57-1901. That's for new units. And I would say here, the practical experience and the recommendation from manufacturers has been that your tan delta, or your power factor at 20 degrees C line frequency, should be less than 1.5 or 2 times the initial reading. And this is one more thing to take into account, the initial reading. sometimes the power factor value that you measure of just the bushing, because you can put your bushing on a tripod, right, and do just a bushing test and do your power factor test of C1 and C2. It may change slightly. I would think that C1 should not get much of an influence at all, but C2 probably will get an influence, because now that it is immersed in oil, now that you have the lower envelope of your bushing connected to the winding on the transformer, you may see a slight change as well on your C2. So it is important for you not just to have the values that may match with your nameplate of testing the bushing outside of the transformer, but it is very important for you to have the record of the bushing as it is installed on your transformer, and make sure that you have that information for the future. Okay. With that being said, when we talk about the confidence of this 20°C line frequency power factor, and now we're going to get into an advanced method, which is basically an advanced application of line frequency power factor, which is our narrow band dielectric frequency response, right? And this is something in between what we have talked a lot, and we have a vast experience working for over 25 years on the full spectrum dielectric frequency response. But we identified that this narrow band, it's important to be part of our routine diagnostic, especially for bushings. So when we do our line frequency power factor, right, it's good, it gives us information. And if we have some limits according to the standard, we will refer to those. What is better for line frequency power factor? Of course, to do some trending analysis, to have some historical values, to look into the history, what has changed, when has changed, right? What is the difficulty here is that temperature, right? It's difficult to determine. And what we have seen is that the methods sometimes to normalize to 20°C, the power factor value tested at, say, 30°C, is not always correct, and that might be misleading. What is better in this case, better than just trending line frequency power factor, is to do what we call the narrow band dielectric frequency response, which is a measurement of power factor values in frequencies between 1 Hz and 500 Hz. And this is very important for you to look, because 1 Hz to 500 Hz is not just a number. It's a band of frequencies that allow us to look not only into the solid insulation system, but also the flexibility and the sensitivity of 1 Hz, okay? And that is much more sensitive than our only line frequency value, 60 Hz or 50 Hz. It is not trending required, okay, if it is properly corrected to 20°C, okay? We will see now some examples down the road in the presentation. But most important for you is that now the power factor piece of equipment that you have is able to run this test. And the most important part you will see in the frequency ranges, how these lower frequencies are much more sensitive. And of course, you can go from line frequency. If you got a high number on your line frequency power factor, then okay, I have a problem. Well, what is the problem, all right? Then you start looking into your narrowband dielectric response, and you identify that that might be confirmed, right? And you may have a non-typical dielectric response, which is a different type of problem, but may guide you to some different solutions, right? And at the end, a definitive way to assess the condition of your high voltage bushing or extra high voltage bushing will be with a full spectrum DFR test that can go from 1 millihertz all the way up to 1,000 hertz. Okay, this is the conclusive solid liquid insulation condition assessment. I want to make reference a little bit on this temperature correction as well, because when we look into some of the limits for tan delta, right, or for power factor at line frequency, Secret, for example, has provided a set of, basically they provide a curve, right, based on the ratio of your tan delta measured at whatever temperature you measured, and the tan delta will be at 20°C. And this is only provided for C1, okay? So there is no correction factors provided for C2, because C2 is not always the best guide, not always the best way to look at the insulation assessment. Okay, so when we do this, you can see here that the tan delta for a new bushing, right? We have limits that have been established, minimum, maximum values. Let's say we decided to have this 0.7%, but we are testing at 0 degrees C. If we measure 0.875, right, that means that with the application of this factor of 125, it's exactly my 0.7%. So just so you have this, right, it's sometimes a little bit difficult to just try to take the information from the chart. You can look at this table. That will be maybe easier for you to look at. What is interesting as well from the information received from that working group is that typical values reside between 0.2 and 0.4. And if you look at the nameplate of your bushings in the substation, most of them are in the range between 0.2 and 0.35. Okay, we have a big database of different testing that has been carried out, not only with power factor, but also with dielectric frequency response in the full spectrum. And again, the nameplates that we see in the majority are, between 0.2 and 0.35. There's some extra high voltage bushings from factory that are coming with 0.4, 0.41. But again, majority resides within this range of 0.2 and 0.4%. So that is a good indication for you that your system might be in good conditions. And then let's look into the narrowband DFR, some field observations. First of all, let's look into the difference in the frequencies. When we talk about power factor testing, right, we're looking about line frequency, and we only look at the information at one point, either 60 hertz, either 50 hertz. That's all we have. And then we need to go into the process of temperature correction. We need to look into the information that we have, probably do some trending analysis, okay? But if we determine that the power factor is over certain number, that you may look based on the references or may look into the expertise of the company. What else? So now, narrowband dielectric frequency response, which is part of the power factor test set, can look into this new frequency range between 1 hertz and 500 hertz. So you can immediately see the difference on the amount of information that you get now from this narrowband dielectric response. And from here, if we need to go into definitive analysis of the condition of this bushing, we will go into the full spectrum dielectric frequency response that will cover the vast range of 1 millihertz all the way up to 1,000 hertz. So you can clearly see now that with narrowband, we can understand much better the dielectric behavior of the insulation, not just on one point, but any change due to aging, contamination, moisture, damage of the insulation system can be better monitored now in this 1 to 500 hertz analysis. So very important, very critical. And many people will ask about timing, and I have a little chart later on for you to look into this analysis. And the time is, let's say, between 3 and 4 minutes. So approximately 3 minutes that you will need to take to run this narrowband test on your bushings. All the uncertainty that you will have with your line frequency power factor because of the changes, if it changed, you don't know if it is because the liquid insulation has a problem or the solid insulation has a problem. You don't know where is the problem. You know that the power factor changed. But narrowband is more sensitive to these insulation changes. And sometimes, especially, we have seen that line frequency may not have changed to a level that you will, suspect any potential damage going on inside your bushing. Narrowband going to 1 hertz gives you that sensitivity. Line frequency requires some trending. Narrowband, you will see that our analysis will provide you some values, right? And if later on you would like to do some training on, say, 1 hertz or 2 hertz or 10 hertz, you can also do that because you have the information anyway on your narrowband testing. Your line frequency power factor has low sensitivity to moisture. And this is important to see because you will have a fast reaction or a significant reaction on your power factor values when you go over, say, 2% moisture concentration or 2.5% moisture concentration. But here with narrowband, that is it's an early detection, and again, looking into the lower frequencies, it's much more sensitive to that. It's your line frequency is used for field evaluation, and results require some expertise. And with narrowband, of course, this is an easier way. You're looking at spending extra 3-4 minutes on your bushing and your transformer testing, but of course brings you much more information that will allow you not only to say this is good or this is bad, but also to, if there is something doubtable, if there's some aging, if there's some progressive change on the dielectric signature, because basically what you see here is the dielectric signature, right, of your component. This is unique to every single bushing, and we will see now on different examples. So basically, this tan delta at 20 degrees C line frequency provides assessment of the condition, right? But you need some limiting values for our trending analysis. The way that we're looking at this, and because of narrowband dielectric frequency response, measuring in this range between 1 and 500 hertz. By the way, when we run the test between 1 and 500 hertz, the voltage with the power factor test set is 250 volts RMS. And we use what is called the individual temperature correction. We have presented that before. If somebody is interested in individual temperature correction, we can talk a little bit more separately. You can send us an email. We can certainly get in touch with you. But that is a way to look not now at a table, a reference that might be for a new bushing, but it's looking exactly into this unique dielectric signature that you get from narrowband, and makes the temperature correction based on that specific condition that you have at the time of the test. So you will have a proper correction, an accurate temperature correction, and therefore a better analysis of your power factor value or any of these frequencies between 1 to 500 hertz. That's the beauty of individual temperature correction. It's not just to correct your 60 hertz. It will correct any point in the dielectric response that we have from that specific specimen. Of course, there's lots of work, as I mentioned, not only running power factor, but also running full spectrum dielectric frequency response. And these units, you can see, for example, on the same transformer, 3 bushings, same manufacturer, same day, same nameplate, same everything, but the dielectric behavior throughout the time may change because there was overloading on one phase, there was a fault on the other phase, there was something different, right? And they may age in different ways. That's the reason why it's very important to look at this information, and at least, if not to have the full spectrum dielectric response, at least to have the narrowband dielectric response. So looking into examples, let's look at one transformer, right? With 3 bushings like I was mentioning before. So we have H1 on the left-hand side, H1, H2, and H3, right? Similar high voltage bushings on the high voltage side. And look at the difference of the dielectric response. Yes, I understand that maybe just looking at the 60 hertz, I would say this is a high number. But if this was shifted, I may have not seen that. But you can clearly see the dielectric behavior of this bushing, which is my H3, versus H1 and H2. So it's telling me that even though I have the same type of bushings for the same amount of time under similar loading conditions, the dielectric behavior is different, right? And you have a different dielectric signature on each one. And you cannot compare, or you cannot normalize your power factor 60 hertz of this bushing and use the same parameter for the other 2 bushings. That would be completely wrong. That would be completely wrong because it's completely different thermal behavior. Now that the dielectric behavior has changed, now the thermal behavior has also changed. In the next one, on your right-hand side, you can see this is an example that we prepared for the presentation at SIGRE. Just 12 different bushings, right? On these 12 different bushings, you can see that 11 out of 12, and I would say that 10 out of 12 are below 0.5%. And let me just put some limits here. So here's your 0.5%, here is your 0.7%, and here is your 1%. So you have 10 units below 0.5%. So are those okay? And then you have 1 unit, right, which is between 0.5 and 0.7. And there's only 1 unit, right, that is over 1%. But now I am able to put all those bushings under the same spectrum and do some comparative analysis, bringing those normalized to 20 degrees C by ITC, not by just a reference table or a reference chart, but looking into the unique dielectric response that each one represents. As you can see, on the 60 Hertz, you barely see any differences. Let me just erase this a little bit here, okay? You can barely see any differences, okay? It's more or less the same values between 0.26 to 0.5, but you can clearly see the discrepancy that you have at 1 Hertz. So 1 Hertz gives you a much better picture. And I would say that the lower frequency you go, the better you understand what's going on with this bushing. So you have, let's say, your starting point right here at 60 Hertz. Then we can look at my 10 Hertz, we can look at my 2 Hertz, and we can look at 1 Hertz. So much more sensitive. I have a better picture. I know that this bushing here, right here, requires more attention than this bushing here. But if I look at the numbers only in the 60 Hertz, both are okay to me. And this is very important. So the idea now is to give you an additional parameter for evaluation. And we look into 1 Hertz, especially because of the capability of the equipment being able to go all the way down to such a low frequency. And you see that typically when we try to compare this 1 Hertz in similar units, right, in sister units, high voltage or low voltage side bushings, typically same manufacturer, typically same year, typically working under the same environment, same loading conditions, operational conditions, you would expect similar behavior, like in this case, right? You see, these are extra high voltage bushings that were tested, and you can clearly see that this dielectric response corresponds to a very good condition bushing, okay? And it's mainly flat. You know, one of the things that you can see in extra high voltage bushings, very good condition, is a very flat response between 1 Hertz and 500 Hertz. In this case, it was moved to only 110 Hertz. But you can see it's a very flat response. Now, let's look at this condition, because a work that was presented about 3 years ago or 4 years ago for Sigre was based on the correlation of power factor, narrow band, and dielectric frequency response on the analysis of OIP bushings with respect to DGA. So I really invite you guys to look into this reference. If you need the link, we can provide the link so you can have a little bit more of information on that correlation between these frequency response techniques and DGA. If you look at this, right, when you look at the first chart, your 60 Hertz, it's basically the same for all these bushings, okay? And we'll use just 4 bushings in this example: OIP 13, 14, 2, and 1. So if I'm looking only at my 60 Hertz, like you see on this column, right, you see for OIP 13, 0.32%, 0.28, 0.31, 0.30, and these are already corrected values to 20 degrees C. What would you say? Everything is just okay, and everything is just good. But when we look a little bit more, right, and we go out of this, we use the traffic light, so the green is very good condition, and we look at the 20 degrees C 1 Hertz, you can see that now my 1 Hertz says, yes, your OIP 13 is okay, your 14 is also okay, your number 1 is also okay, but this one, OIP 2, excuse me, there is something wrong with this bushing. So I would suggest you to do a full analysis. So something that I was not able to capture on my line frequency power factor, now it's been captured when I go to 1 hertz on my power factor or narrow band dielectric response. And it took me only 3 minutes to get to that conclusion. So I hope I'm being able to convey the information and the importance of this narrow band dielectric response, especially on this narrow band and 1 hertz ability that you have now to provide a better sensitivity of the changes on the dielectric response. As you can see here, again, these are decades, right? We're looking into logarithmic scale. So if you look between 10 and 100 hertz, this is the amount of information that you can get. Between 1 and 10 is exactly the same amount of information from one decade to the other decade. And that is the beauty of being able to look into these lower frequencies below 10 hertz, between 1 and 10 hertz. One more thing here. We have, again, 3 bushings that are mounted on a transformer. You can see slight changes going on at 1 hertz, right? But mainly everything looks flat, everything looks good in these 3 bushings. When we look at this one here, even the numbers at 1 hertz don't seem to be too high, but you can clearly see that there are differences on the aging process of those 3 bushings mounted on the same unit. This one has an increase on losses, okay, but that one is not my main concern. My main concern in this specific example will be the orange bushing right here, because that deviation, that change on the shape to what is typical, this is my typical, I always call it like a smiley face, a very serious smiley face, okay? But this one here on this side, as you can see here, there's a non-typical, there's a hump, and that might be related to some conductivity, okay, inside the installation system. Something is wrong, something is contaminating my system. I want to explore in more detail this bushing, okay? And that's something that probably I would have missed testing only my 60 hertz value here. When we look into this individual temperature correction and DFR, of course, it's critical. First step, as I mentioned before, is not only to look into this, but it's only to think about how much information I can really normalize and how can I normalize. Tables might be tables, it might be for a new bushing, manufactured bushing, but the aging process will be a little bit different, okay? So I really encourage all of you to look into individual temperature correction. We can provide you more information about it. Maybe not enough time today to go through all of that. And look at the hookup, right? When we are doing a DFR or a narrowband DFR test, it's basically the same connection, right? You will energize from the high voltage side, you will measure from the test tab, right? You're looking into the C1 insulation. Look at the graph that we have here. 4 bushings mounted on the same transformer, and you can see my H3 and my H2 look pretty good. But what about H1 and what about H0? They don't look as good, right? There's a high losses here, but is that good? Is that okay? How can I say that? Well, if this was already corrected to 20 degrees C, these guys at 1 hertz show a number that is greater than 1%, and that for us is a trigger. But on top of that, what I want to emphasize in this part of the presentation is that the temperature correction is completely different. You will see your H1 bushing, and remember the H1 bushing is one of those that were in bad condition. The temperature response that we get from this unique dielectric response obtained from that specific bushing shows us this thermal behavior. When we go to a good bushing, right, in this case the H2, look at the difference on my thermal behavior. A completely different thermal behavior for my power factor testing. So again, you can look into any table, but it's much better if you look into the unique dielectric signature that your system has at the time of the test, right? And that way you can have a complete different approach when you do your ITC correction. In this case, we're going from about 37 degrees all the way down to 20 degrees C, right? That is the behavior, and that's the beauty of the ITC, that we can shift not only one power factor value, but the entire dielectric response. And another interesting thing is when you're going into extra high voltage locations where noise is the issue running this test. You can see in this example, for example, we know that when you are in a high voltage substation, you may have not only AC but also DC noise, right? This is just an average from different substations that we have tested. You can have an AC influence of about 0 to 100 microamps. On DC, you can have 0 to 50 nanoamps. And if you go and try to measure at very low frequencies with low voltage, a very low capacitance, the current that you try to measure is very small, and that will be affected by the noise. And you can see in this example here, the red line that we have, the red curve, below, say, 0.2 hertz is being influenced by the noise. But when we crank up the voltage with an amplifier and we provide 1400 volts, 1.4 kilovolt, we get a smooth curve, and that is the one that I want to analyze. So keep this in mind, because not everybody is in a place that there's no noise in the substation. So for your DFR, the limits that we suggest, right, as new, are here: 0.15 to 0.5 on the solid insulation moisture, liquid insulation conductivity. We are in picosiemens per meter, so look at these numbers. I'm not going to read all the numbers, but this will be for your reference, of course. And one of the interesting things is this is the power factor 1 hertz, corrected properly by ITC, okay, to 20 degrees C. That is the value, that is important value that now I can look with my power factor test set and get this number. And we recommend to have as new as 0.5 to 0.5. There's a range for good, there's a range for aging, right, and an average condition. And, you know, I struggle a little bit with the terminology when the terminology says this is a severe condition and this is an extreme condition. I think that if you get into these values, the first approach should be to contact either the manufacturer of the bushings, or come to us, come to the Megger specialist and ask about your results, because I just don't like to scare people with this is extreme or this is super critical and you need to take off the system immediately. So just look into this. I think that it's better to say investigate, and if it goes into the investigate, is a warning call for you to, before you energize, take an action and do some more research. Okay, so just to put quickly the differences, of course your narrow band is between 1 and 500 hertz, approximately 3 minutes, right, and is ideal for immediate comparative analysis on bushings mounted on the same apparatus and to determine if there's any deviations from the limit that we have provided on 1 hertz. So you now have additional frequencies to look at. On the wide band, of course, we can typically run, because the dominant material in bushings is paper, sometimes we don't need to go to very low frequencies, but I think that in average we can go to 5 millihertz, 10 millihertz, all the way up to 1000 hertz at temperatures close to 20 degrees C, right? And that will take only 12 minutes to do the full test. The beauty on the equipment is that you typically, this DFR test is run only at low voltage values, 140 volts. But there is technology, and we have the technology to look at 1400 volts. So you crank up the signal to noise ratio 10 times. This is very, very critical. And just to finalize my presentation, I want to get into some general conclusions. First of all, bushings is an important component in our system, right? It's basically the link between the high voltage system or switchyard and the transformer or my circuit breaker or whatever piece of equipment. But it's making that change of stage, change of insulation media from air to oil, from SF6 to oil, from SF6 or air to air, whatever that is. But it's there to protect, and it's also part of the fire protection of my high voltage major equipment. So reliability of operation cannot be compromised, and that is critical. Then if you go from your power factor, look into your power factor values. Do not forget about your bushings. Look into your narrow band. It's only 3 more minutes on your testing procedure that you need to add. But now you will have a much better understanding, not just about one point on your on your analysis on 60 hertz. But now you can look into frequencies between 1 hertz and 500 hertz and do the analysis on any other frequency you want. But we have provided here, especially because of the sensitivity that we have identified on 1 hertz, certain limits that will help you make the call and make some warning call and trigger your attention if there's something that you overlooked with just power factor testing. Use ITC to normalize your analysis. ITC is the individual temperature correction process. We're not going to get into details. We don't have the time today, but we will be more than glad to discuss the abilities of individual temperature correction, not only for bushings, but power transformers and other equipment. To improve the signal to noise ratio, if you can see, don't try to analyze signatures where you have ups and downs on your dielectric response, especially at lower frequencies. Please don't do that, because you may get into completely awkward analysis and misleading assessment. The way to go with that and to overcome the noise is to apply a voltage booster or an amplifier and improve the signal to noise ratio. And of course, remember that the DFR provides an efficient method to assess moisture and contaminants, including PD byproducts. And this is one interesting thing, that sometimes you may see a high level of moisture, but especially when we talk about bushings, it might be related to contaminants, right? And type of contaminants, especially we have seen X-wax to give a very similar dielectric behavior as it does moisture in the system. So just that for you to keep in mind. With that being said, I just want to highlight some of the technology Megger has for narrowband dielectric response. The Delta 4000, it's a fantastic piece of equipment that has been in the field for over a decade. We have a dedicated capacitance and power factor test instrument that is capable to go all the way up to 12 kV. It allows you to do the narrowband test between 1 and 500 hertz. It comes with the individual temperature correction feature, as well as voltage dependence detection, which is another great feature. We may talk on some other time about voltage dependence in power factor testing. Our multifunctional tester, which is TRAX, and you're familiar with TRAX. This is not only a transformer test set, it is a substation test set designed for transformer, instrument transformers, circuit breakers, different devices in the field that you can test with this. To me, is a portable laboratory. Really is the best tool for troubleshooting in the field. And again, it comes with a module. This module here is my high voltage module that will allow me to go up to 12 kV and do my narrowband dielectric frequency response, my ITC, and my VDD. Last but not least, a unit that we are very familiar with and has been in the market for the last 24 years, and it has created for us a huge database of information, and we are able now to look into, the correlation between power factor, line frequency, the narrowband, and the full spectrum DFR with the IDAX. And IDAX has the beauty of being a system that has been for such a long time in the market, an excellent reputation, and being used by most manufacturers of power transformers. And you can see also that it has the ability of using the amplifier, so you can use a full spectrum DFR up to 1.4 kilovolts RMS. With that being said, I go back to you, Michael. Thank you very much for your attention. Ready for questions.
All right. Thank you, Diego. So at this time, the presentation portion of the webinar is officially concluded. We'll now take some time to answer as many of your questions as possible. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. When you have a moment, if you could take some time and fill that out for us, we really appreciate hearing your feedback so we can continue to improve upon future webinars. On the survey, there's also a field where you can request a quote or a demo on any Megger products. A copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for our upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar, You Ask, We Answer, a panel discussion on transformer testing. All right, now let's get to your questions. Our first one I'm going to be directing to Sanket Bolar. Sanket, many of the bushings I have come across no longer have the C2 tap adapters. What is your recommendation for connecting the C2 tap without the proper adapter?
So I can only speak with respect to our instruments, and we provide different types of adapters. These come in various shapes and sizes. They can be used on different types of bushings. So we provide these adapters as accessories along with our power factor test sets. Besides that, if you want to do C2 measurements, then we also provide a special adapter, which is basically a banana pin on one end and a little alligator clip on the other end. So that banana plugs into the high voltage cable directly, and you're able to perform C2 measurements easily without having to get into. You're able to get in tight spots, which is typically the case when you're making a connection on the test tap with that adapter. So we have all these different types of adapters that makes it really easy to get a solid connection and a clean connection on the test tap, which is necessary to get a good measurement, be it C1 or C2.
Thank you, Sanket. My next question I'll be directing towards Jill Duplessis. Jill, besides temperature, what other test variables may influence my bushing test results?
Okay, so a few come to mind actually. So I would first say one of the test preparations is to short circuit each bushing on a singular winding together. So most windings enter and then exit the transformer. So at a minimum, you should have 2 bushings to short together on any given winding. If you have a typical Y or delta connection, 3-phase, then, of course, you're shorting 3 or maybe 4 bushings together. If you don't short circuit the bushings, and they probably are, because it's a step to that preparation detail you want to attend to do a power factor measurement anyway, and so then presumably you're going on to test the bushings. But if they're not short circuited, even at line frequency, this can influence your bushing test results. Typically, we'd see the middle phase bushing influence the most, but all 3 bushings, if say you had a delta winding, all 3 bushings would be influenced, whereby the power factor would increase, the middle one the most, due to capacitive coupling between the bushing under test and its 2 neighboring bushings. So you want to make sure, if you can, that you have the winding short circuited, the bushing terminals shorted together. But this will also affect dielectric response as well. It would show up and influence bushing test results at other frequencies as well. We've seen where the resonance of bushings will be in the range of 100 to 400 hertz if you're not short circuiting those bushings. So you want to make sure you do that. Another test variable that could be influencing your results is if you don't have a good grounded flange on a bushing. So sometimes, like if the bushing is installed in, it's painted or something like this, where the flange loses that good connection to the grounded tank, that would influence results. And then a big one is, of course, surface leakage, right? And so that's not only influencing line frequency bushing test results, but other frequencies as well. So I'm talking things like if you get salt contamination on a bushing, or carbon, or high humidity is another frustrating one. So if you're over 70 to 80% humidity, that can certainly influence your results. So you would want to, anytime you get suspect results, measurements on a bushing, you definitely want to put an eye towards eliminating some of these test variables before you assign too much value to the test results and assume that it's a problem with the bushings. Definitely take care, or definitely, clean the bushings with non-alcoholic containing cleanser, dry the bushings if you think it's humidity, make sure you're shorting the winding, things like this, before you evaluate your results. Thank you.
Thank you, Jill. Next question I'll send over to Diego. Diego, what about NBDFR on bushings on single-phase transformers? How do I do comparative analysis? Forgot how to read there for a moment. I'm sorry.
That's okay. Okay, so if you have a single-phase transformer and you have one unique type of bushing mounted on this transformer, of course, you might not be able to do a comparative analysis with similar bushings on the same transformer, but the question would be, don't you have probably another sister transformer with a similar bushing to look at? The other thing is, if you do have that kind of condition and you're doing a narrowband DFR, we can help you. You can send us the measurement and we can help you on the analysis, right? And look into our database, depending on the type and manufacturer of the bushing. That is something that we always assist our customers with if they don't have something to compare against. But also, I think that with these limits that we have provided, and that is part of the beauty of this narrowband technology, if you do properly your test, if you run your 1 to 500 hertz, you look into the limits that we have provided, those are the first triggers, right? And if you have more questions, of course, just give us a call, and we have a fantastic technical support group in North America, all over the world, really, to assist you with that kind of question.
All right. Thank you, Diego. Sanket, why does power factor vary with frequency?
So the DFR that Diego covered in this presentation, basically we are looking at the varying values of power factor that we get with the changing frequency of the voltage that we apply across the bushing C1. The reason why this happens is because of polarization. Mainly, there are different types of polarization which occur, and the polarization mechanisms depend on the frequency of the voltage being applied. Now, in the frequencies that we look into when we do DFR or narrowband DFR, we are looking at mainly interfacial polarization, which occurs in a composite dielectric, and OIP bushing is an example of a composite dielectric, which is made up of oil and paper. So when we get into the frequency ranges of 1 hertz to 10 hertz, any increased conductivity because of the presence of moisture or contaminants greatly contributes to a higher value of a particular dielectric constant, which translates to a higher value of dissipation factor or power factor. And that increase in dielectric losses associated with the increase in conductivity translates to a higher value of power factor, which is why you see the power factor climb up drastically in the lower frequencies when you're dealing with a bushing which is in the early stages of deterioration.
Thank you, Sanket. Diego, where can I find a reference for limits and standards?
Okay. As I mentioned during the presentation, you have different references for general concepts on limits, right? So I would suggest first SIGRE 755, the technical brochure, to look into that one for limits. That is the first guide. Of course, you will see limits for OIP, RIP, and RBP bushings mainly. All are related to a 20° C value, okay? So that's where, again, it is important to remember, how do I normalize the power factor value that I have tested at whatever temperature and bring it to 20° C. And again, that is the beauty of narrowband DFR and the application that we have in our testing equipment with the delta unit or the trax unit, that you can do the correlation, not only the measurement, but also bring the information to 20° C. The other thing is, we can look, for example, if you're looking only at the line frequency values, again, you can look into IEEE C57152, right? That will give you the information for service units, right? Service age units. And if you're looking into information for factory acceptance, you need to look into the IEEE C5719101. So those three documents, three standards, will give you the only line frequency values. If you want to look into other frequencies, you can come to us again, and we can provide you the information. Actually, this presentation will give you the reference for the 1 Hertz value that we are suggesting you also include into your analytics. Mm-hmm.
Right. Thank you, Diego. Next question is for Sanket. Sanket, how is it recommended to obtain the temperature of the OIP bushings?
So we assume that the temperature of the bushing is somewhere in between the ambient temperature and the top oil temperature. So you will, to be precise, you have to take the average of the ambient and the top oil temperature of the transformer. The ambient temperature, by the ambient temperature, I mean the outside temperature. So typically they are going to be pretty close to each other, but if you're testing on a day where the bushing has just been taken off the service and it's pretty cold outside, then there may be quite a bit of a difference between the two. But the ideal way to do it, or the best way to do it, is to take the average of the two temperatures.
Thank you, Sanket. Next to Diego. Does NBDFR provide insight in capacitance changes in bushings, or is it restricted to % power factor?
That is an excellent question, and thank you for asking that. I think that we focus right now on the sequence of power factor from the line frequency value to narrow band having 1 to 500, and from full DFR going from 1 millihertz all the way to 1 kilohertz. But of course, one of the things that we can look at is not only power factor. Dielectric response per se is a tool that will allow you to look into capacitance and dissipation factor or power factor. And it's a very interesting question, especially I personally like to look more at the capacitance changes during, for example, a dryout process on power transformers. So I always look into my dielectric frequency response of the capacitance rather than the tan delta. Okay, and it's a little bit more complex than that, because you will have a real component of the complex capacitance, and you will have an imaginary component that both are equally important to look at. But just to put it in a simple way, yes, capacitance is important, and narrowband will allow you to look also at capacitance changes if there's any. You would expect as a function of frequency, especially in the range between, I would say, 100 hertz and higher frequencies, to have a very linear response, right? And then between 1 hertz and 10 hertz, you may have a little tilting up, right, of your capacitance, and a little bit of change on that. So yes, absolutely, narrowband will allow you to look not only into the percentage power factor changes, but also on the capacitance changes. Yes.
Thank you, Diego. Next to Jill. What is the recommended frequency for doing NBDFR on OIP bushings?
Okay, another good question. So I look at narrowband DFR as a routine diagnostic test. So I would supplement, anytime I'm doing power factor testing on my bushings, I'd be supplementing them with narrowband DFR. Your test connections are the same. It's very little investment of extra time to do it, and yet it gives you so much kind of future-looking information. In fact, I would say that I sometimes think about online monitoring of bushings, and the fact that online monitoring of bushings are watching in real time, quote unquote. I mean, whatever that period might be, maybe every 5 minutes or what have you. But it's looking just at the power factor measurement. And I just, it emphasized that narrowband DFR, some of these early problems that are developing, while I can't give you a timeline for every single case, I mean, it's conceivable that a problem could start to emerge and be seen at some of these lower frequencies, a good bit in advance than when power factor is eventually affected. So I would say to this, definitely routine. And then I would go on and supplement my answer by saying, you know, I've seen some cases. So if you've got I'll just give you an example. If you had you're at a power plant maybe, and you've got a situation where the bushings are enclosed in isolated phase duct, you know, and maybe it's a poor application of the bushing, and you know it, but you need a replacement bushing, and so you go back with one that's not rated for high temperature or something. You know, after running that bushing for maybe 6 months, I'd be for sure saying, you know what, let me do a narrowband DFR measurement on it, see how this bushing has been impacted. Anytime you know you're in a situation where your bushings are, you know, being taxed really heavily, I would say to if you had the opportunity to do narrowband DFR, I might do it a little bit more frequently than what a normal, like Diego presented, that 3-year average is seeming to be from the Seagray report or survey what people are adopting. You know, you look at how your asset is applied, and then, you know, sometimes you might be more aggressive with how frequently you're doing the measurement. Thanks.
Thank you, Joe. Next to Sanket. Why NBDFR tests better than DFR or LPF?
So I don't think Diego said that at any point that narrowband DFR test was better than the other two, that is full-blown DFR or line frequency power factor. What narrowband DFR provides is an option of an additional test, which certainly gives you more information than the line frequency power factor. And this test can be done by standard power factor test sets. Line frequency power factor has been done on bushings for close to, I mean, right from the beginning, right? It's been done for decades now, more than easily over 60, 70 years. So people have been doing this for so long, and they're going to continue doing that. But then you have these power factor test sets which are capable of doing narrowband DFR in addition to a line frequency power factor. So you do not deviate from tradition, but at the same time you do an additional test which gives you that additional valuable information, which helps you in detecting early deterioration in bushings. So you do more without doing what you've without abandoning what you've been doing so far. With the full-blown DFR instrument, with a full-blown DFR test, you're going to need a separate instrument which does that. It also does line frequency power factor, and the measurement obviously includes narrowband DFR. But the line frequency power factor test is done at a lower voltage of 140 volts, which can be amplified to 1.4 kV. But you're not doing it at 10 kV, which is what line frequency power factor is done at when you do it in the traditional way. Right, so that's why narrowband DFR, that's what makes narrowband DFR stand out, because it's a test which can be done with a standard power factor test set in addition to the line frequency power factor.
All right, thank you, Sanket. It looks like we're out of questions. If you think of anything else, please feel free to contact us offline. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. Once again, I'd like to thank you all for attending, and I hope you have a great weekend.
Thank you, everyone. Enjoy your weekend.